And I came extra early today to get donuts from outside, and I missed it. He's always putting the boxes away. What time when did you get here? You got a donut this morning, did you?
I think I got one of the last ones.
You did. God, you gotta come early. It ruined my day. It ruined my day. I really did. I came 10 minutes early. I'm gonna get one. All right. So we're right in the middle of this, right? We're doing FMA, F equals mass times acceleration, right? It is YouTube Friday. We will get to YouTube. One of the problems we're gonna do today involves some YouTubing, so we'll look at that shortly. So this is, we did some of the force, I guess we just did Cartesian coordinates. F equals ma. We laid out a procedure on how to solve these things, right? In Cartesian coordinates, you just get these three equations of motion, sum of the force in the x, y, and z, and they're equal to mass times acceleration in their respective directions, okay? We went through how to solve these problems. This procedure stands for any of the coordinate systems that we do. So today we're gonna do normal tangents, still do the same thing. We're gonna do a free body diagram, we got a checklist for that, and then you have a solution procedure. We're going to do a free body diagram. Based off that free body diagram, we're going to write down the equations of motion in all relevant directions. We're going to do kinematics as required. Sometimes it's really involved, sometimes it's not. Okay, and then we're going to solve. Okay, so we just did that for Cartesian coordinates. What we ended up with last time, right at the end of class, was this derivation for what we do in normal tangent coordinates. And so in this case, it's the same. It's a really brief. A really brief derivation, right? We just have normal tangent just to review. You got a tangent that's going tangent to the path, and then you've got a normal direction that's going normal to the path, right? And they're perpendicular to each other. And we have acceleration defined in each of those directions, right? Our total acceleration vector is going to be AT in the ET direction, and which is the AT is the change in velocity with respect to time. It's just your change in speed, right? It's like stepping on the gas as you're going around this curve. That's going to cause a change in AT. And then there's also AN, which is the centripetal acceleration component, and that's if there's any change in direction, there's acceleration associated with it. And so AN in this case is either going to be v squared over rho or rho omega squared. Right? And that's it. I mean, that's it for the derivations. We're going to sum the forces in the t direction, and that's going to be equal to mass times acceleration in the t direction, which is just mass times the change in velocity, right? And then you look in the n direction, and the sum of the forces in the n direction is mass times acceleration in the n direction. And so it's either going to be the acceleration in the n direction, it's either going to be this guy, mv squared over rho, or m rho omega squared, depending on which we have. If we're dealing with a problem that we know omega, we'll use the one on the right. If we have the problem, we have velocity, we'll use the one on the left, right? Simple as that. And then you can always you can always move back and forth between it, right? And it's all based off of velocity being equal to rho times omega, right? Velocity is equal to rho times omega, and that's how that conversion is happening. Okay, that's it. So let's do an example, right? Right? Again, sometimes you just have problems that it'd be easier to solve via one of these other coordinate systems. This would be an example, right? This car's beautifully drawn car here, right? Traveling like this. Somebody sent me this. I drew this car, and then somebody sent me this, right? This is a real car. When the car you used to draw in kindergarten pulls up beside you, right? That's pretty close. I'm a terrible drawer. I don't think that's not too bad, though. That's one of my better drawings, okay? So that car's traveling like, it's a circle, right? It's traveling in a circle. Doing this with Cartesian coordinates would be a pain in the ass. Doing it with normal tangent coordinates will work better, okay? And so what we're trying to find is so this car's traveling like this, and we want to find the real problem statement said the max speed that the car could travel without leaving the surface. But that's also a more fun way to think about it, the minimum speed required to leave the surface, which I think is a little bit cooler, a little more interesting. Okay, so let's do it, right? And so at this point, you're like, oh my God, what do I do, right? Well, what we do is we stick to the plan, right? What was the plan? What's the first step we do when we do the plan? Free body diagram, right? It's just literally, I mean, all these problems, before you even like think about too much, it's like, I'm gonna follow this plan, right? We're gonna do a free body diagram. F, B, D, right? So you isolate your mass. In this case, again, with all particles, it's just gonna be a dot. Okay? What we got acting on this? Gravity. Right? Mass times gravity. Anything else? Normal force. Kind of. We'll talk about it in a second. Normal force. Is that it? That is it. Right? If this thing, if they were stepping on the gas and accelerating, right, there would be, some sort of thrust coming here, right? But in this case, it's going at a constant speed, right? If they did say, they're accelerating this thing, there would have to be some force in the t direction causing them to accelerate. But in this case, it's just a constant speed, so there is that's it. That's all there is on in terms of forces on this. But we're not done with our free body diagram because we're also going to now label our coordinates, right? So our coordinates, the ET and the EN direction. Which way do you think ET and EN are pointed here? And so this is traveling around a curve. The problems we've done before, we were kind of looking down on it, but now we're looking at a cross section. But it's traveling along a path like that. So our tangent's going to be going this way, and our EN's going to be normal to that. And the normal to that path in the direction of the center of curvature, right? So what that would look like down here, we would have ET going this way, ET hat going that way, and EN hat going this way. No real dimensions to put on there. Radius of 200 feet, I think it's what it says, 200 feet, but nothing really worth putting on our free body diagram. So our free body diagram's done. All right, now we go to equations of motion. I guess is what I was calling that. Equations of motion. Okay. In this case now, we have two different directions. We have the ET direction and the EN direction. So we write our equations of motion in each of those directions. All right, we'll look at the T direction first. Right. Sum of the forces in the T direction is equal to MAT. Right. And we look back up at our free body diagram. There are no forces in that direction. Right. So that's 0. And which means that we're not accelerating in that direction, which means this is equal to 0. Okay? So there's nothing happening in the T direction. Again, if there was some sort of force, a thrust forward, then there would be acceleration. Or if they told us there was an acceleration, that would mean there would be a thrust force. They go hand in hand. Okay. More interesting, N direction. N direction. And sum of the forces in the N direction is equal to mass times acceleration in the N direction, which is equal to mv squared over rho. Right? Because we're dealing with velocities, not necessarily omegas. Okay. Do you get to that? That's our equation of motion. Now what we're going to do is, what are these forces, right? We're going to look to see what are the forces in the N direction. Here's a look up at our free body diagram, and I've got a positive mg because it's acting in the direction of En, and I'm going to have a negative n, right? So it's a negative n acting in the negative En direction, a positive mg acting in the direction of it, and that's it, okay? So when we expand this sucker down below, this is going to be mg minus the normal force is equal to mv squared over rho. Almost there. Okay. What we're after, if you recall, we're after the velocity, the minimum velocity required to launch this thing. So if we just take a second and look at this equation right here, right? So you just, right, I summed my forces and I made it equal to mass times acceleration. That's what's different this time versus Cartesian. Instead of just setting this equal to like the change in speed in the x direction or something like that, you set it equal to the acceleration in these coordinate systems, which is just v squared over rho. Right? So that's the big difference there. But we just look at what we know, right? I know the mass of my car. I know gravity. I kind of don't know normal force, so that'd be kind of an unknown right there. And then what I'm after is that velocity right there. and I'm going to know the rho. So I know everything in there except for velocity and the normal force. But I kind of know something about the normal force. What's the normal force going to be in this situation? 0, right? Because we're trying to find, right? We're trying to find the point, right? The cusp of this thing taking off. It's going to take off when that normal force is equal to 0, right? You know, if you were going slower, then you would have a normal force there. And then if you're going faster, the way we set up our equations right now, our normal force would be pulling down. It would end up with a positive normal force if you solved it, which would say that it would be going down, which would not happen in this situation. A roller coaster or something where you're attached to the rails, you could get the normal force acting out. But in this case, the cusp between flying and not flying would be that normal force equal to 0. So at this point, we come in, we put that normal force equal to 0, right? Because it's taken off, and so we get mg is equal to mv squared over rho. The mass is actually canceled for both sides. And you could solve for velocity, right? You could put in all of our known terms. 32.2 minus v squared. And then the rho in this case is 200. What did I do? Oh, equal. This is an equal sign. Right. And this gives us an answer of a velocity equal to 80.2 feet per second. This would be a very classic example where units might be nice to use, right? I hate them. I don't know why. It's a bad habit to get in, but I do. I just make sure everything's going in feet, and then I know that this thing is going in. This has got to be feet per second squared, and then I know that my radius right here has got to be in feet, right? And then your forces are going to be in pounds. I'm just very consistent with it, and I just know. Again, if you're having troubles with it, use your units. That's a better thing to do. You're not all doctors like me. I'm a doctor. I reminded my kids that this morning. My son was like, "Hey, do you think he's got to miss school today?" And he's like, "Do you know how to use, or do you help me with my geometry homework?" It's like, I'm a doctor. Of course I know geometry homework. But then I looked at the first page. It's like, yeah, I don't know how to do that. But I think I got it though. All right, next problem, a little more interesting. Okay, 1,000 pounds of people jump from a bridge, 200-foot rope. Capacity of the rope, 2,990 pounds. Is everything going to be okay? All right, this goes along with the video. Kenny Bunker.
Right over the edge. T-minus 10.
I want to get the whole thing in.
Way to go, and that's right over the edge. T-minus 10.
The plan, drive to a predetermined spot on the bridge, attach a 200-foot-long cable to a parked limousine. The 5-member stunt squad runs the swing end of the cable to the side of the bridge. Each jumper would attach themselves to the end of the cable.
You notice camcorder on his head?
Swinging out like a pendulum. Then release the cable and escape before police, Coast Guard, and fire department authorities can capture and arrest them all. The stunt required precise execution. The camera crew in the helicopter is ready. The camera crew below the bridge is set.
He's got a full camcorder on his
Devils, jump.
Okay. We're going to come back. Okay? Do you see the technology I had to grow up with? That guy's got a literal a full-on camera strapped to his forehead. Okay? Now you got his little teeny GoPro stuff. Anyways, all right. I think you guess this probably is not going to go well. Okay, so let's do some calcs here and see what went wrong. Okay, so they've got this rope. By the way, I went down a big rabbit hole. There was a full 2020 episode on this stunt, and I watched the whole thing yesterday. And they do interviews with all the participants and everything. And It turns out he did no math. He was just like, that'll probably work. And then they all jumped off the thing. Okay, but say we were to do some math, right? So all these people are standing up here, and then they jump off, right? And then they do a big old swing, 200 foot radius on that thing, okay? And so we're like, is everything gonna be okay? 1,000 pounds of people jump from a bridge, 200 foot rope. Is everything gonna be okay? Okay, so again, what do? Stick to the plan, right? The sticking to the plan, we're gonna do a free body diagram. Now let's do it right down here. 1. F, B, D. Free body diagram. Right? And then there's lots of stages, right? I mean, where do you draw your free body diagram? In this situation, we're just going to draw it at some random location on the way down, right? As a function of theta. Theta is going to be changing as it goes, right? So we're just going to draw our free body diagram. It sometimes doesn't, most of the time it doesn't matter where you draw it, at what position you draw it. So, right, there's my 1,000 pounds of people, okay? What's all acting on those people? Gravity, right? Gravity's almost always there, right? Mass times gravity is that way. And then obviously the rope, right? When it's not broken, right? And we'll call that tension. Tension in the rope. That should be it, right? I mean, those are the ones. I mean, technically there's wind resistance, but we're ignoring drag, right? So we're just jumping off, and this is all that's acting on it. Tension, force, and mass times gravity, okay? Coordinate system, right? We have to put in our coordinate system. We have tangent to the path. I'm gonna put it down here, right? They're moving along that path. Oh, I don't want it curved. Call that ET hat. And then I have normal to the path this way. Okay, so we've got our forces in there. I've got my coordinate system in there, but I do need to label some angles, okay? Because that's the last little step. We're almost there. Just got to label some angles. MG to this side. So we're going to call this theta right there. And then this thing's going to get broken down into multiple components. Let's use purple. All right. I know I'm going to need these later, so I just kind of draw them on here. All right. My MG, right, it has two components, right? It doesn't, T lines up in the EN direction, but MG doesn't. So I always like to put those on there just so I know that they're there. There's going to be a little bit of this MG. A little bit of MG is going to be in the ET direction. A little bit of the MG is going to be in the T direction. Right? It's going to be a function of theta. Okay. And then I'm going to go a step further and label. Oh, I want to know that angle right there is going to be theta inside of there. Okay, this is my geometry right here. If this angle right here is theta, that one's not theta, which means that one is theta. I do it. That's my little trick in my head. It's like theta, not theta, theta, not theta, right? And you just keep working your way around. It's way too hard to figure out 90 minus theta, but my son's gonna do fine in his geometry. I'm gonna teach him tricks like that. Theta, not theta, theta, not theta, not theta, not theta. We'll do that a lot this semester. Okay, that one's theta. Okay, all right. I mean, there's our free body diagram. We got it all there. Okay, so now let's write down our equations of motion. 2 E O N's my equations of motion. Right? I got two of them here. I got some of the forces in the N direction. I don't know why I started with N direction, but I did. Some of the forces in the N direction is equal to T, right? And I just come up here and I say, what is in the N direction? Well, I got T going in the N direction, and then I've got this little guy right here. Right? Just those two. Right? And so I got T, it's in the positive T direction because it's in the EN direction. Sorry, it's a positive T because it's in the positive EN direction. And then this is a mg sine theta. Mg sine theta is that little part of mg in that direction. And it's negative because it's acting in the opposite direction of n. Cool. That's equal to mass times acceleration in the n direction, which is equal to mv squared over rho, or m rho omega squared. I'm going to use this one, but we'll come back to that in a minute why we're doing that. But that's it, okay? There's my equations of motion in that direction. That's one equation that I get to use. I get one more equation, right? We don't have enough to solve it at this point, right? So we have to look at the other direction. Sum of the forces in the t direction is equal to, we look to see what's acting in the t direction. I've got this guy, right? That's it. It's going to be mg cosine theta. Mg cosine theta is equal to MAT, which is equal to M times R alpha. Okay. I want to point out too, right? I always do this along the way. I always like to just highlight what are we after. We're after this. Okay? We're after that tension force. We want to see if that tension force, the worst case tension force, is going to be bigger than 2,999 pounds. Okay? That's what we're after. So it's always nice to, as you're going along the solution procedure, is just remind yourself, where is it? Where is it? What am I after? Where's it at? Yeah.
What's big R in this case?
Oh, big R is the 200. It's this. Yeah, good question. That's.
Okay, were you gonna use that or you're gonna use rho?
Oh yeah, I wasn't done yet. It just so happens that this is R, and that is R. Yeah, thank you. I was just gonna say what's rho, but that's whatever you want. I mean, I'm gonna keep doing it. I'm gonna keep doing it all semester. I don't care if you find it funny. I find it funny. Okay. That's all that matters. That's all that matters. Okay. So we're after that T, right? And so I'm looking at this. So I almost know everything, right? I know my mass times gravity. I know they kind of, and then I'm after, if I knew the velocity at the bottom, I could get what T is, right? If I knew the velocity at the bottom, I could get what T is, right? Because at the bottom, right, and we can all agree the worst case force is going to be when that sucker's at the bottom, right? Right? We can all agree that. So technically, I know T, or as I'm after T, I'm going to know the theta that I'm after. It's going to be the theta that gives me the one at the bottom, right? And then I know my radius. If I knew the velocity or I knew the omega down at the bottom, if I knew that, then I could get what my tension force is. Okay, so then I look in the other direction. I look in the T direction. I have to get there somewhere. Okay, and now I'm almost there. Well, I'm kind of there. I got mg cosine theta is equal to m times acceleration in the tangent direction, which is m times r alpha. So I have an acceleration equation there, right? I can just rearrange this bottom part, and I just say, I cross some terms out here, right? The masses on both sides cancel out, and then I can get alpha as a function of theta, right? I just rearrange that equation, and it gives me alpha is equal to g cosine theta over r, right? And this is an acceleration, a function of position. Right? Acceleration, a function of position. Right? It's alpha, a function of theta, right? And we talked about how you solve these problems, right? So from this alpha as a function of theta, I can then go and get my omega, right? I get my omega by going to my little cookbook of what do I do when alpha is a function of theta. It involves using the chain rule. So by the way, I'll show you in a second, this problem absolutely, again, screams work energy, right? It absolutely screams work energy. I got all this potential energy of these 1,000 feet of, and they jump off, and all that potential energy goes into kinetic energy, and I could real quickly in one line without doing a single integral, calculate the velocity at the bottom, okay? But we don't know how to do that yet, so we're gonna do this integral thing, okay? But just a little foreshadowing, that's where we're going next, okay? All right, so then alpha is equal to d omega dt, which is equal to d omega d theta dt. This is omega. And so then you rearrange it, alpha d theta is equal to omega d omega. Plug in our alpha term there is g cosine theta over r d theta is equal to omega d omega. I'm going to integrate this. I'm going to integrate this. Okay, I'm after the omega. So this is being integrated with respect to d theta. And so I can put some bounds on this thing. This thing is going from 0, okay, up at the top. Right? Up at the top, this theta is going to be equal to 0. Right? It's going to be straight across up at the top. But then when the people jump off, it goes all the way down. That theta, again, at the bottom is where the worst case scenario is going to be. This is going to be pi over 2. And it's going to open it all the way up. And down at the bottom, that angle is going to be pi over 2. Right? And then it's starting out with 0. It's starting out at rest, so that omega here is going to be 0. And then this is going to be, we'll call that WF up there. Right? And that's what we're after when we solve this. We're after what this WF is. Okay, I'm after that. Right? And if I go through and carried out that integral, which I did on my calculator, I get my omega is equal to 0.567 rads per second. Okay, which means absolutely nothing to me. I don't know, is that right? Right? I was like, right. I mean, I need to know it. I could do it now, right? This 0.567, right? This 0.567 goes, right? It'll go up in there. That goes, now I know that omega, that how fast they're gonna be going. The worst case scenario gonna be down at the bottom, right? So 0.567. What is that in terms of velocity? And remember, I mentioned this earlier, and we haven't talked about it much yet, but the velocity is equal to r times omega, right? We've used that a couple of times. That's that relationship. That's where the v squared over rho, or v squared over r, and rho omega squared. It comes from this. It just comes that the velocity is defined as r times omega. Right? We'll use this a whole bunch when we get into rigid body stuff. You'll get very used to that. But that's it. I could do that. If I carry that out, right, I could say that's 2. You don't have to do this part. I'm just doing it. Just so you can see. Just so we can get a feel for how fast they're going. So this is 113.5 feet per second. Right? Which also means nothing to me, right? Like, it's 113.5 feet per second fast? I don't know, right? So if you calculate, if you went into miles per hour, this is equal to 77.4 miles per hour. Okay, well, it's pretty fast. Right? It's pretty fast. I mean, it's not super fast, but it's pretty fast, right? 77 miles per hour. So when they jump off the top, when they jump off this top, they're going to be going right down at the bottom, right at this point right here, because that's what we got for right at the. We solved this for when theta is equal to pi over 2, which is going to be down at the bottom there, and so it's going to be going 77 miles an hour when they come down around that corner. It's not so bad. Okay, so but let's do that. Let's go. Let's find the forces now. I guess 3 would be solve. Is that what step 3 is? Or no, kinematics. Oh yeah, that was our kinematics right there. This is kinematics. Right. Kinematics was right there. So we did use them, I just forgot to call them out. okay? And step 4 is solve. Okay, I'm solving this. So we go back up to that original equation, T minus mg sine theta, mg sine theta is equal to m r omega squared. Right, and you plug in all our known values, T minus, you gotta be careful of this, right? Mg, oh yeah, Mg is 1,000. Be careful of that, right? Mg is the weight. In English units, right, we always talk about when you tell somebody's mass, you say that their weight, you don't tell what their mass are because we have a stupid unit called slug that's floating around, right? And so you don't give people's weight in slugs or their mass in slugs. You give it in their pounds, and so then you got to put it in terms of slugs when it goes into these equations, right? Sometimes, I learned that this has a name, sometimes you want it in terms of where gravity's in inches per second squared, and that, anybody know what that's called? Is when it's called a slinch, which is, I bet you didn't know that existed. I didn't either until last year. Somebody pointed out in class that when you divide your weight by 32.2 times 12, which is 386.4. So you take your weight divided by 386.4, the unit you get is a slinch, which I called bullshit and I was wrong. It is real. There's a unit called a slinch, a slug but in inches. Our Australians, right? This is stupid, isn't it? Right? We're got kilograms and newtons and shit like that, right? But instead, we're doing pounds and stuff. So you got to be careful. So in this case, our mg, I'm going to do things in feet per second squared. My mg is just going to be 1,000. The two together, the weight. Mg is the weight. So 1,000 times sine of theta, sine of actually pi over 2. Okay, because I do know what that is equal to. Now though, see now I got the mass there. Right? I got that mass there, and I got to do 1,000 divided by 32.2, right? That's what my mass is going to be. The radius, again, is 200, and then this is 0.567, I think, right? Is that what I had? 0.567. Okay. And so I plug this bitch in my calculator, right? I don't want to think about it. I don't want to do any algebra. Just beep, 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 beep. Did I do something wrong? Oh, and I wasn't done yet. I was just going to say, what did I forget to square? And I forgot to square that omega. Right? Just going to say that. Right? And what you end up with is T is equal to 3,000 pounds. Okay, so I think I like this way. So, right, I mean, so we did it, right? We solved for that tension, and then at this point, I can compare that tension right there to what was allowed, right? Or what the how much allowable tension force is in that cable, which was 2,999, right? So this would say that right around near the bottom, this thing should break. Okay, this should break when they're going 77 miles an hour. Now, there are other ways to do it, right? We could have gone in and said that T is equal to 2,999, and we could have solved for the speed that would require to get that, and you could compare that to the speed that you're getting. Usually in like engineering, you do it this way. You look at the demand versus the capacity, right? The demand in this case, I calculated that, and I compare back to the capacity, which is 2,999, which means that we're gonna have a problem. Okay. Any questions about our solution process and stuff like that, right? Again, this one absolutely screams work energy, and I did it via work energy yesterday just to mess with it, right? Just to show you, this is we're gonna learn this next, right? I look at my energy at state 1, I compare it to the energy at state 2, and then I can solve for the velocity, and you get the same velocity, right? It's not a single integral involved in doing that. Okay, there's integrals involved in the derivation of work energy, but you get to skip it when you do work energy. Okay, so let's go back to our video. It says there's gonna be a problem. Let's see what Kenny, how bad Kenny was. Okay. It doesn't look that bad, except for they're going 77 miles an hour.
The Daredevils did not have enough pressure on the cable when they jumped from the top of the
Okay,
bridge.
okay. All right. I take it. That's not the problem, right? We just calculated, right? It said, the guy just said in the background, if you didn't hear it, he says the reason it broke is because when they jumped off, they didn't have enough tension in the cable. They didn't have it taut when they jumped, and so there was like an impact load on it. But you can see there's no impact load on that because it gets tight right away. It's right at the bottom of that curvature, the centripetal acceleration. There has to be a force pulling back up with enough force so that it causes the acceleration back towards the middle. If there is not enough force there, then it's going to break. Let me show you something. This, no joke, popped up yesterday in, it's embarrassing, but my Instagram Reels. No. I used to be a TikToker. I swear to God, I was a huge TikToker. The problem is TikTok is too addicting. I just get sucked in. They just bring me in, and then I'm just embedded in there. I can't get away. So then I go to Reels, and they suck. And so then I get out. I get out. But then I heard though that it'll learn. Right? It learns like what you like, and then the Reels will get better. Right? But here's the kicker. Is my wife constantly sends me reels that suck. And so then I watch those reels. Okay? And then it throws off my algorithm. So all I get is weird parenting. It is weird quirks that happen while you're parenting, right? Like that's all that happens. So it's a good system now. So now I don't spend much time in reels. Okay. So this one, I swear to God, this showed up yesterday. So this is what happens when you don't have enough tension in the rope when you jump.
5, 6, 7, 8. Don't even think about it. Go. Okay, Lionel, you got it.
Okay, that situation, that is what he explained, right? That there was not enough tension in the rope, and that's what that failure would look like. Okay, we'll watch it one more time. Is that? Wait, so I don't get banned from YouTube. Don't do this. That's the problem. I'm going to show you something today that you should not do. Don't do this. And don't do the other thing either.
5, 6, 7, 8. Don't even think about it. Go. Okay, Lionel, you got it.
Okay. See? Okay. So that didn't have enough. That's not what happened here, right? This happened here was, yep.
The 5-member team weighing almost 1,000 pounds reach the end of the cable. The tremendous force snaps their lifeline. For the jumpers, the first injuries are whiplash from the cable. The second and more powerful
this is an interesting
impact
view.
of the water 200 feet below the bridge.
Right.
Lori is unconscious, her neck broken. Jeff is not breathing. His neck is also broken. Chaos takes over as the jumpers and the boat crew stare at death all around them.
So side note, everyone lives, everyone fully recovers, right? But how about that, like the narrative, right? It's broken. So-and-so's not breathing. Their neck is also broken, right? Yeah. Okay. So they didn't make it. Let me see. Yeah. This is so there's a full 2020 episode on these guys. Steve Trotter. Yeah, I mean we won't watch the whole thing, but they do a full interview.
Skyway Bridge. He gets the call. Lieutenant G is astonished that 5 lives were riding on an untested steel cable, no thicker than your little finger.
There were no professional stunt people. There were no mathematicians, no physicists in the group at all.
He just sent it. He just sent it.
Impact, only rookie jumper Kenny Bunker is still alert.
I wasn't even dazed in the slightest. I was
Kenny's ready, man.
But Jeff Sargent and Lori Martin, the woman who was unusually quiet, are both unconscious and not breathing.
So as soon as my head came above water, Lori and Sarge were both face down, arms out. So I rolled him on his back, and Lori.
Anyways, if you were looking for something to do tonight, right? Friday night, right? You can watch a little video. Yeah. Let's share one more. I got a couple more that popped up yesterday. This one popped up yesterday too, right? So I like the scream. I like the scream that happens. He doesn't get hurt. They can't ban me for showing this one. That was funny. Okay, don't do that either. Don't do that either. And then this is dynamics related. This showed up as well. See, Reels is learning from me, so. That's an interesting one, right? Your lifetime's average velocity would be 0, which is true, right? If you only use those 2 data points, right? It would only work. Okay. All right. Any questions about this stuff? Okay. This is very practically related, right? Or very practical information we're getting here, right? He did nothing. He did no calcs. He's probably like, this cable should work, right? And then they went for it. So be careful who your friends are. Okay. So let's just do this quick little derivation. I'll set us up for doing a little bit more complicated problem. So this is our last coordinate system, right? Some of the forces in polar coordinates. F equals ma in polar coordinates, right? And again, what these coordinates look like. Is I've got a vector that points to the particle, and then I'm going to have a coordinate coming out of that just keeps going. Right? That's going to be ER direction, right? And then one in the direction of E theta, perpendicular to that. Right? All right, when things are traveling in circles, this coordinate system just puts it's right on top of the normal tangent coordinate system. You could use either one at that point. Okay, and in this coordinate system, our velocity is defined as such. Right? R dot in the ER, R omega in the E theta. Right? And then what's more interesting to us in this situation is what the accelerations are. Right? R double dot or minus R omega squared in the ER, R alpha plus 2R dot omega in the E theta direction. Right? And then this is, we're actually going to do this in 3D, so this is cylindrical coordinates. So you could also put in, we're also going to put in that third component, which would be would turn it into a cylindrical problem. So there'd be you'd have a circle going this way and then a depth associated with it. Okay. So when we write our equations of motion, again, we just look in the 3 different directions in this case, 3 directions because we're doing cylindrical coordinates, right? R direction, some of the forces in the R, is just mass times acceleration in the R. And so you just take the component right here that's in the ER direction, that acceleration, and just put it right there, right? So some of the forces in the R is equal to M R double dot minus R omega squared, okay? You do it in the theta direction, you do the same thing. You just substitute in what our A theta is. R alpha plus 2R dot omega. Okay? And so same solution procedure as what we used before. Okay? These will just be, now we're going to have three equations of motion. Right? So the forces in the R, the theta, and the Z. And so you draw your free body diagram in those coordinate systems. You sum your forces from your free body diagram. You set them equal to mass times their respective acceleration. So you just write this, when you do in the R direction, you just mass times acceleration in the R. You just write this sucker. Okay? Massive acceleration in the theta and massive acceleration in the Z. Just do it just like that. Okay? And then what we'll do next time, right, is we'll solve this problem. I don't want to start this one today, right? But this would be a case where this thing is spinning around in a circle, right? with that omega, it's spinning around with that omega. You can imagine if omega gets really big, that collar can slide up and down on that rail. That collar will go up. If I don't spin it at all, that collar is going to slide down. And so what it's asking us for is how fast does that need to go in order to hold it at that position right there. Okay, and you can see this is going to be a 3D problem. We're going to have to do the 3 directions, right? Because if you looked at this thing from above, that would be traveling around in a circle. That's where our polar coordinates would be. Like if I was looking down on it, our polar coordinates would be that way. But then there's this up and down that can happen as well, which is the acceleration in the z direction. And so we'll solve this problem. And you're like, oh my God, how would I do this? You don't need to know. You don't need to know how to do this. All you need to know is the procedure. A free body diagram, write down our equations of motion in the 3 directions, apply any kinematics as required, and solve it. Literally just pops out every time. It's so clean. I mean, look how clean these solutions are. Look how clean these bitches are, huh? Hey, even with terrible handwriting, look how clean that is. So again, strive. It's always hard for me to say. Strive for this cleanliness, right? But do, right? Some of you are beyond this, and then don't strive backwards. But if you're below this, push for this, right? Because we're engineers now. We're known for being anal and concise and all this stuff, and it's for a reason. We're actually doing very dangerous things. That people's lives are at risk and stuff like that. I have a colleague of mine. When you get to structural engineering, if you mess up on a calculation that would kill someone, he has a stamp that has a big skull and crossbones. So he just throws it right on there. It's like you just killed someone, right? It happens, right? It absolutely happens. Please, so take this serious as you move forward, right? So cool beans. All right, break. Have a good weekend.